All right, so today we have an example video. This is a companion to lecture 7, and we're going to do an example of using the context-free pumping lemma to show that a language is not regular. Excuse me, is not context-free. So this is going to be a lot like the pumping lemma. The structure of this lemma is very similar. So if you're curious about the logic involved, it might also help to watch the pumping lemma video because the argument we make is going to be very similar using this slightly different lemma statement. You can also check out CFPL pages 128 and 129 for examples, including this one. So let's consider the following language. C, this language C equals A to the I, B to the J, C to the K, such that 0 is less than or equal to I, is less than or equal to J, is less than or equal to K. So strings in this language look like A's, then B's, then C's in increasing order of length. So we'll always start the same way if I'm trying to prove that this language is not context-free. So I will assume, for contradiction, that C is a context-free language. And we will get to a contradiction from here. So by our assumption, C satisfies the context-free pumping lemma, which means the following is true. There exists some number P such that any sufficiently long string S in the language with S being greater than or equal to P in length, that's the sufficiently long part, can be divided into S equals U, V, X, Y, Z, that is 5 concatenated substrings, satisfying. And then we have 3 conditions just like in the pumping lemma. Our first condition says for each I greater than or equal to 0, U, V to the I, X, Y to the I, Z is in the language. 2, BY, these 2 strings that can be pumped, at least one of them has length 1. Put together, they have length greater than 0. And 3, V, X, Y. That's our central part. Our 3 substrings in the middle are at most the pumping length. So this is what the context-free pumping lemma tells us is true about every context-free language. So C is not context-free, but we're assuming it is. We are giving ourselves the consequences of the pumping lemma, and then we are trying to spool out those consequences until we get to the point that we find a contradiction. That contradiction, that impossibility, is going to show us that our assumption is false. So to contradict, if we want to contradict the statement above, we have to find some string S. So the context-free pumping lemma is telling us a thing that's true for every sufficiently long string S. We're going to find a string S for which this should work and for which it doesn't work. So we're going to find a string S for which we can't make this starred part hold. So we'll find S in C with S greater than or equal to P that can't be divided in any way satisfying our 3 conditions. So I'm going to show one string that won't work for us. Let's see a candidate A, B, B, C to the P. This is a string which is indeed in the language, and it's also has length at least P. The context-free pumping lemma tells us that all sufficiently long strings satisfy our three conditions. We have to find at least one string for which the conditions don't hold, but this is not a good candidate string because we can, in fact, divide it in a way that satisfies the conditions. So if I write out A, B, B, and then a bunch of C's, so this is our string, one way I can split it up is I can make this U, this first C, V, bunch of the rest of the C's, X, this last C, Y, and then I'll make Z equal to the empty string. And if I split my string up in this way, it's true that Vy has length greater than 0. It's also true that Vxy has length at most P. In this case, it has length exactly P. And finally, if I pump, I can pump down, which will decrease the number of C's by 2, or I can pump up. Every time I increase I, I'm increasing the number of C's by 2 because I'm duplicating V and Y. Unfortunately, for all I greater than or equal to 0, we still have more C's than B's and more B's than A's. So this is not a good example for contradiction. So the reason I'm jotting that down is because occasionally you will find strings that can be pumped. That doesn't mean that my language is necessarily context-free. It just means that I have not been able to find a contradiction using that string as my contradiction string for the pumping lemma. Now I'm going to pick a slightly better choice. A to the P, B to the P, C to the P. And if you were to pick this string, if you were solving this problem, you wouldn't necessarily know that this would be a great choice for contradiction ahead of time. But there are a couple of things about it that would give you some clues. So it does have length at least P. It is in the language. It also has this property that it's right on the knife edge of satisfying the language's condition. So I, J, and K for this string are all exactly equal. What that means is that if I increase B or C, if I decrease B or C or increase A or B, I'm going to have a string that's not in the language. So not only is this a string with 3 large parts, A, B, and C, there are also parts where if I change them just a little, I'm going to get a string that's not in the language. And that's why I might suspect this is a good string for contradiction. So now let's consider whether or not we can divide this string into 5 parts that satisfy the 3 conditions. So suppose we divide A to the P, make this string S, B to the P, C to the P into UV, X, Y, Z. So there are a few cases we have to consider because we want to rule out all of the possible ways of dividing this string. For example, case 1, we'll consider what if V and Y both contain only one type of alphabet symbol. So in other words, I've said, this is the case in which I've broken up A to the P, B to the P, C to the P into 5 parts. And my substrings V and Y both contain only A's or only B's or only C's. Well, one of 3 things are going to be true. One possibility is that there are no A's in V or Y. This is what happens if V and Y only have B's and C's. Then U, V to the 0, X, Y to the 0, Z to the 0 equals UXZ is not in my language, as this decreases the number of B's or C's. So again, I've made two assumptions. I've looked into one specific subcase. I'm looking at divisions where V and Y both contain only one type of alphabet symbol. By condition 2, I know that they have to contain something. Vy is greater than 0. But because I've specified they only contain one type of alphabet symbol, some type of alphabet symbol is missing. If the type which is missing is A's and I pump down, that is, I remove V and Y, I get a string that has either fewer B's or fewer C's than A's, because I'm decreasing the number of B's or C's without decreasing the number of A's. I might have something like A to the P, B to the P minus 2, C to the P. So that division is not going to work. You can also look at a couple of other similar cases. 1B, no B's in V or Y. If Vy contains A's, then U, V, V, X, Y, Y, Z has more A's than B's. If Vy contains C's, then U, V, V, U, X, Z has fewer C's than B's. So again, I've broken down into some very specific subcases. I'm assuming V and Y only contain one type of alphabet symbol. If they don't contain any B's, then they have to contain A's and or C's. If they contain A's, then if I pump up, I've got more A's than B's, and that's a problem. If they contain C's, then when I pump down, I've got more C's than B's. That's also a problem. Finally, another case I might consider, no C's in V or Y. Here, U, V, V, X, Y, Y, Z contains more A's or B's than C's. So if there's no C's in V or Y, then they must contain some A's or some B's. So if I pump up, I'll increase the number of A's or B's. And that will mean that I have more A's or B's than C's. So again, breaking this down into subcases, trying to rule out every possible division of my string into substrings. I claim I've covered everything in case 1, every possibility where V and Y both contain only one type of alphabet symbol, the case where there's no A's, no B's, or no C's. So case 2, I'll consider the opposite of case 1. Either V or Y contains two kinds of alphabet symbol. So any cases that don't fall into case 1 will fall into case 2. And if I want to look at this visually, again, we'll have a bunch of A's, a bunch of B's, and a bunch of C's. Perhaps I have a division like U, V, X, Y, Z. And in particular, I know if I'm in this case, then either V or Y straddles two different letters. But I claim that this also can't be pumped. The reason why is U, V, V, X, Y, Y, Z now contains some symbols out of order. In my picture above, if I pump V and Y, then I've got something like an ABB followed by another ABB. I've got A's after B's, which is a problem. And something like that will be true whether V or Y straddles either the AB gap or the BC gap. So any way of splitting my string S equals A to the P b to the p, c to the p into u, v, x, y, z breaks one of my three conditions. So how do I know when I'm done? Well, if I were to look back over my argument, I should be able to convince myself that my cases cover every possible division of a to the b, p to the b to the p, c to the p into u, v, x, y, z. What I'm trying to show, I'm trying to contradict the pumping lemma as stated here. So I got to find some string that cannot be divided, right? Got to show this thing in two. So what I've done is I've carefully plotted out every possible case of a division, and I've shown that all of those cases must fail at least one of the three conditions. Implicitly, a couple of times, I've used the condition vy greater than 0, which means either v or y must have some characters. And I've also used the condition vxy is less than or equal to p to rule out the case where v or y contains all three kinds of alphabet symbol. So it's not possible for either v or y to contain a's, b's, and c's, because that would require my substring vxy to be at least p. So conditioned on those two things being true, all of my divisions fall into case 1 or case 2, and I see that all of them will violate condition 1, the pumping condition. So that allows me to conclude any way of splitting my string into u, v, x, y, z breaks one of my three conditions. It follows that C fails the context-free pumping lemma, and therefore C is not context-free. So if you're sitting at the end of this video and you still think, wow, that was a lot, it moved fast, we covered a lot of cases, how do I be certain that my proof is working well? I'd suggest taking the following steps. The first thing I would do is try to absorb the statement of the context-free pumping lemma and figure out for yourself, convince yourself that if we can prove this statement too, it'll contradict the pumping lemma. So if that sinks in, you'll know why we're trying to prove some string cannot be divided in any way, and why that's a contradiction to what the pumping lemma tells us. Once we know that, once that statement is solid in your head, all we have to do is carefully build up a logical case that there's no possible way for our candidate string to be broken up correctly. I had to trace out a lot of cases here, but if I had just come up with this string, there's a couple of ways I might argue it to myself. At a high level, before I'd even written the proof, I might think, look, if I break down this particular substring into 5 pieces, and then I start pumping it up, it's going to quickly change the number of A's, B's, and or C's. And it seems like doing that is going to break the precise relationship of the length of my 3 strings. It's either going to increase A or B without increasing C, or it's going to decrease B or C without decreasing A. I haven't proved that, but that's what I will be gunning for before I even start. So then what I'll do is I'll just have to be careful as I work my way through this part, make sure I've covered everything that's going on here. So thank you for watching, and I will see you in class.